Hello and welcome back to Ordinary Differential Equations, the video series where we talk a lot about solving differential equations and talk about the theory behind it. And in today's part 13, we continue our discussion of the Picard-Lindelöf theorem by considering an example and a so-called Picard iteration. But as always, before we start, I really want to thank all the nice people who support this channel on Steady, here on YouTube or via Patreon. Please note, only because of your support, it's possible for me to create such mathematical videos here. And of course, you also get something back for that. You just have to click the link in the description to find additional material for all the videos. Okay, then let's immediately start with the topic here, which is again the so-called Picard-Lindelöf theorem. We have discussed and proven it in the last video, so let's give it a quick recap here. It states that an initial value problem of this form here has a unique solution if a local Lipschitz condition is satisfied. So it definitely answers the question we had about the existence of solutions. And in fact, we already knew before that a locally Lipschitz continuous function gives rise to unique solutions. And I should also tell you here that we get the existence of solutions also under weaker assumptions. However, this is not so important right now because this description of Picard-Lindelöf is sufficient for our context. Also, it has the advantage that we can use the Banach fixed point theorem to find a solution. This means the iteration formula we stated in the Banach fixed point theorem can be used to approximate this solution alpha. We just start with any function we can call alpha tilde. And then, if we apply the map phi n times and send n to infinity, our solution alpha should come out. And here, please recall that the map phi was just defined with this one integration. However, this implies that doing this composition n times means that we have n integrations in a row. Okay, and now I should tell you that this approximation process for a solution is often called the Picard iteration. And indeed, you see it's not magic at all, because it immediately comes out of the proof from the Picard-Lindelöf theorem while we applied the Banach fixed point theorem. Therefore, I would say it's very helpful to look at an example. And let's look at an ordinary differential equation where we already know the solution. So I want to take the initial value problem x dot is equal to x. In other words, the vector field V is simply the identity map. And maybe, to keep it simple, the initial value should be 1. Okay, and now for the Picard iteration, we have to start with a function alpha, so we could either guess a good one or we start with a simple one. And please note, the only thing that alpha tilde has to fulfill is this initial value equation. Therefore, what is always possible is to start with the constant function. Hence, we can simply set alpha tilde of t is equal to 1 for all t. Okay, and then in the first step, we simply apply phi to this alpha tilde. So we get phi of alpha tilde is equal to 1 plus the integral from 0 to t of alpha tilde. However, alpha tilde is constant, it's equal to 1, so this is a really easy integration. Namely, the integral is just equal to the length of the interval, which is equal to t. Hence, the new function that comes out here is 1 plus t. This means, in the next step, we have to put this function into our map phi. Hence, in this second step, we have the new function inside the integral. Indeed, the starting value x0 is always the same, only inside the integral we get some changes. However, it's still an easy integration because it's a linear function. So you see, here we should be careful. We cannot use the same variable name t, so maybe we use s as before. Okay, and then we can solve the integral and we get t plus 1/2 t squared. And again, this is our new function we put into our map phi as well. But maybe at this point you can already see the general formula for the nth step here. Moreover, then you should also be able to prove it by induction. More precisely, if you repeat this integration, you see the next term would be 1 over 6 t to the power 3. And then we would get the power 4 and so on until we get the nth power of t. And then it turns out that the factor in front is indeed 1 over n factorial. So this is very good. By having this general formula, we can look at the limit n to infinity. More precisely, if we fix the input t here, then this is a pointwise limit for functions. And in fact, we see that this pointwise limit exists and we get a nice function out. More concretely, it's given by an infinite series. It's not so surprising, but it's a very common series. Namely, it's exactly the formula for the exponential function. Hence, we can write this is exp of t. So now, in summary, we see that we have a pointwise limit for this iteration, and it's given by the exponential function. But we also know that the iteration phi n alpha tilde converges by the Banach fixed point theorem. And this means there is a unique uniform limit for this convergence. And now, since the uniform convergence is stronger than the pointwise convergence, we already know that the uniform limit has to be given by this pointwise limit. So in short, doing the pointwise limit here is enough because we know by the theory that it is also a uniform limit. So we don't have to show that in the example because it's already given. Okay, with this I would say now you know how the Picard iteration works. And with the next videos I want to go more into the direction of geometry again. Namely, we can discuss what Picard-Lindelöf implies for the orbits in our pictures. So let's meet again and have a nice day. Bye bye.